So I just want to show you a couple things that you guys might not have seen before. And this one right here is about reading it. This is write a linear function for f, if f of 1 is 3 and f of 4 is 0. It doesn't give us something that we're used to seeing. There's two things that you need in order to write a function of any line. You guys know what those two things are? Not domain and range. You slope at a point or a point and a point. You could have 2 points or a slope and a point, and then you could write a linear equation. Are we given those things right here? No. Yes, we are. This is why I need to show you this. This right here means 1, 3. You plug in 1, so I know that's the x. Your result is 3, so I know that's the y. It doesn't show you, it actually plugging in 1. It just says if you plug in 1 to the function, you get 3. So what's the point for this one?
4, 0.
4, 0. So there's your 2 points. Can you guys write the linear equation now? A linear function? Heck yeah, you can. Let's find our slope to be 3 minus 0 over 1 minus 4. And so you get 3 on the top, you get negative 3 on the bottom, so it's negative 1. My slope is negative 1. Now I need a form that I'm going to write it in. And the best one to start off with is point slope. You start with point slope, you just plug stuff in. So let's go y minus y sub 1 equals m times x minus x sub 1. Okay, well, guys, give me my x sub 1, y sub 1. What's going to be my x sub 1, y sub 1?
4, 0.
It doesn't matter which one. 4, 0? Okay, we'll do that. 4, 0 is my x sub 1, y sub 1. And so now I plug it in. I get y minus 0 equals negative 1 times x minus 4. And now I multiply stuff. Sweet. This kind of just goes away. You have y equals, multiply negative 1 to both of those, we get negative x plus 4. Bam. There is your slope-intercept form equation of this function, this linear function. Now if you want to write this in standard form, you would add x to both sides, use the inverse operation, so we have x plus y equals 4. Both of these answers are acceptable and right, but you need to know how to switch between them just in case you look down at your answer choices when you're doing the multiple choice and it says it in standard form or slope-intercept form. So let's take a look at some of our functions. We have the constant function, we have the linear function, the quadratic, and the cubic. Okay, the constant function I think is the most interesting because it confuses the most people. This one right here, let's see, we'll go g of x equals 4. If you were to make a table for this constant function,
Wouldn't you just put 4 on the y-axis?
you go like this. Let's see, let's plug in a couple of different numbers. We'll plug in negative 3, we'll plug in negative 1, we'll plug in 0, 5, and 10. If I plug in a negative 3, what do you get? So let's see. G of negative 3, and on the other side there's a 4. What do you get? Oh, 4. If I plug in negative 1, what do I get? Oh yeah, 4. If I plug in 0, what do I get? Oh, 4. Actually, you just keep getting 4s. Because there's no variable over here on the other side, so it's constant. It's constant. It will always be 4. Now let's look at the next one. A linear. Now this one doesn't have any extra numbers on it. The slope is 1 and the y-intercept is 0. But we don't have to write those things. And this function's nice because whatever you plug in, you get out. So if you plug in a 3, you get a 3. It just repeats itself. This function up here, the constant one, that one would be straight across at 4. This function, the linear function, since there's nothing else happening to it, it's a vertical line with a slope of 1, y-intercept is 0.
That's what I thought.
Sorry, I didn't mean to say vertical. I meant to say diagonal. Good, thank you. Good looking out, students. All right, here we go. That's a quadratic. They look like this. And then this one right here, that's the cubic. The cubic function, I say it looks like an N. But it doesn't when you don't have anything else happening to it. It just has the endpoints. Okay, but I say it looks like an N because it kind of does. If there's other things happening to it, like if you had plus 2x squared, then that might make the graph look more like this. Actually, we did it in the DNA. It looked like that, didn't it? Kind of like one of the graphs that we graphed looked like that. It had like an N-type look to it.
What's the last function called?
It's called a cubic. Okay, now let's do these ones right here. We have the square root function, or radical function. We have the absolute value function, and we have, I think on the paper I gave you guys, this is called the greatest integer function. But I like to think of it as the floor function. You should write that down, the floor function.
Which one?
This one right here, the floor function. Okay, the reason why I like to think of floor is because it floors the numbers. Let's go out of order. Let's do this one first. So this one, for this function, if you plug in something like a 1, you're going to get a 1 back. If you plug in something like a 1.2, you're going to get a 1 back. You see how like it floors it. It just goes down to the nearest integer. If I go 1.8, what's it going to give me? It's going to give me a 1. If I go 2.1, what's that going to give me? A 2. And here, let me get a little tricky on you. What is, now let's do another one. 4.6. What's that one? 4. It floors it. Okay, it sends it down to the nearest integer. Okay, let's look at this next one. This next one is going to be negative 1.2. It floors it. Brings it down to the next integer. What is it? Negative 2. Yeah, it's because it's negative, and so it looks a little different. It's not just taking off the decimal, it's going down to the nearest integer. So what would this one be? Negative 0.3. That would be negative 1. Okay. Now, what does this make your graph look like? It makes it look like it has steps. If you guys look at the handout I gave to you, it goes like this. Kind of looks like that. This should not overlap though, so let me delete that. That shouldn't overlap. Okay, that's a floor function. Kind of looks like steps. Now, I call it a floor function because they also have one called the ceiling function. But you guys don't need to worry about that. Let's just do the floor function for now. The square root function, the graph looks like it's taking off like that. And the reason is, I mean, think about this. The x values that you would plug into this, let's think. I could plug in a 0 because the square root of 0 is 0. Actually, you could plug in a 1, you could plug a 2 in, and you could get a number if you plug a 2 in, but we don't know that in our heads. We'd probably do it in our calculator, or there is a long way to do it, but we're not going to do that. Give me another number to plug in the x that's nice and pretty.
16.
4, 9, 16. Those are the numbers I heard. So you get 2, 3, and 4. You see how the y is only increasing by 1 each time? But look at the x's. The x's are dramatically increasing. And so when you do that, your line starts stretching out like this and slowly rising. The absolute value function, I'm sure many of you guys are aware of this one. It looks like a V. It's kind of like the quadratic. It's like a cousin of the quadratic. And the last one, the inverse function, looks something like this. Let's see. You guys could plug those into your calculators and check them out.
Did you just walk in the wall?
Okay, so that's our library of functions. But here we have a piecewise function. Let's graph this bad boy. This bad mamma jamma right here. Did he say mamma jamma? What is that? Okay, these are conditions. Those say, like this one right here. The x has to be less than or equal to 1, so you would plug it into that. And that would look like this. Y equals 2x plus 3, but I'm pretty sure you guys are aware of that. The bottom one is y equals 7. What kind of function is this bottom one?
Constant.
That's a constant. What kind of function is this top one? It's a linear function. Okay, so we'll make a table of values, and you can pick random x's. But my x's aren't going to be so random because I want to pick x's that will fit on my graph. Because when I draw my graph, let's see, graph. Okay, I want to pick numbers that will show me what happens around the 1. And so, let's see. Let's pick a negative 1. Let's pick a 0. And there's my 1. 1's pretty famous right here because he's in the function. Then we have a 2, then we have a 3. Okay, so for the negative 1, if I plug in the negative 1 to this function right here, what would I get? What would f of 1 be for this function? Well, I'll take the 1. Which one does it satisfy? Wait, the negative 1. Dang it. I was saying negative 1, did I say 1? Okay, which one does it satisfy? The one on the bottom or the one on the top? It satisfies the one on the top, so we're going to plug into this one. If we plug negative 1 into that, what do we get?
1.
See, negative 1 times 2 is going to be negative 2 plus a 3 is a? 1. Uno. So I write 1 right here. If I plug it as 0 to my function, which one do I plug it into?
The bottom one.
Let's see. 0 is less than or equal to 1. Yes, that's true. So I plug it into this one right here. So I plug a 0 into the x. 0 times 2 is 0 plus 3. What does that give me? 3. So if I plug in a 0, I get a 3. If I plug in a 1, what do I get? Wait, which one do I plug it into? The top one. I plug a 1 into that. That's 2 plus 3 is 5. And then if I plug in a 2, ooh, this is what business changes. What's what? It's the bottom? Yeah, because it's greater than 1. So what does that equal? 7. What about the 3? If I plug in a 3, what do you get?
7.
Ah. Okay, so negative 1, 1 is right there. 0, 3 is right there. And then 1, let's see, 1 goes up to 5, so that's 3, 4, 5 right there. I got to move this graph down a little bit. That'd be cool if you could actually do that on your paper. That'd be sick. Okay, now 3 is a 7 and 2 is a 7. So if I go 2, 1, 2, 3, 4, 5, 6, 7. I put a dot right here and a dot right there. If I plug a 4 in, I'm going to get a 7. If I plug a 5 in, I'm going to get a 7. And it keeps going like that, right? Okay, but when we do our graphs, we draw lines. Why? Because we want to represent all of the decimal x values. We don't really want to plug in the decimal values, but we want to represent them. So I have a question for you guys. What about this space right here? What are these numbers?
7.
That's like 1.1 and 1.2, right? Which function would I use for those?
Top one.
Let's see, 1.1. See, 1.1 is greater than 1, so I would do that one. So it's a 7. So 1.2 would be,
7.
and 1.3 would be,
7.
so these would all be 7. So this line has to go right there. But there has to be an open circle right there. Why is that an open circle?
Because that's where it stops.
Yeah, it stops right there. Sometimes your piecewise functions have holes in them. This one does not have a hole in it. Because when I get to 1, I have an answer. And when I get to 1.1, I have an answer. If your function has a hole in it, it would look something like this. Let's say it goes like this, hole, and then shoots off like that. 1 is undefined for this function. Why? Because when I go up, there's a hole right there. There is no connection to it. Your hole could look slightly different though too. Your hole could look like this. So now at 1, there's nothing there and there's nothing there. There's a hole. 1 is not part of the domain. That's it.